Good morning, everybody. Duncan's talk leads brilliantly well into the things that I'll be presenting today. This is mainly a structurally focused talk. It draws on some of the most recent work that we've been doing in the structural group at Getech, which is where I fit in. I've been at Getech for 7 years working as part of the structural group. So I'm going to draw on some of our most recent work that we've been doing obviously with a particular Africa focus for today. So I'm going to briefly introduce you to some of our Africa data sets and our reports. Then I'm going to talk mostly about our tectonic evolution studies and give you a brief overview of some of the workflows and methodologies that are applied within those studies. And then that sets us up nicely to look in a bit more detail at some of the study highlights, particularly for the most recent of the studies, which is underway at the minute, which is the East African Margin study, which is due for completion at the end of July. I'll draw on some examples from Somalia and the Horn of Africa and Mozambique. So just a brief introduction to the data sets. These blue polygons highlight the outlines for our three most recent tectonic evolution studies. We have the Equatorial Atlantic, South Atlantic and East Africa, which, as I mentioned, is due for completion in July. Our tectonic evolution studies are focus studies, really. They form the foundation for all of our other studies within Getech, whether they be petroleum system studies, play fairway analysis. The tectonic evolution really forms the framework for all of those. Duncan mentioned, particularly in the Equatorial Atlantic, some of the divergent margin segments of the Equatorial Atlantic and the rift mechanics and asymmetry of these segments really is crucial for the amount of accommodation space available for source rock deposition and subsequent reservoir deposition. So it just shows the application of doing these studies into all of the petroleum systems work that we do. We also have a range of broader-based multidisciplinary studies, which we call our geodynamics and petroleum geology studies. These cover, this is just a selection of our Africa-focused studies, but again, we have Equatorial Atlantic, South Atlantic and East Africa, and we also have a focus study for the East African rift system, which was predominantly an interpretation from SRTM and Landsat data, but also includes the full prospectivity of the East African rift system with some basin-specific case studies as well in there. All of our studies, no matter what the scope, are underpinned by our extensive gravity and magnetic database. Our primary interpretations are based on a suite of derivatives. This is just an example of the isostatic derivative and one of the bandpass filters for the East African margin. You can see that highlight some of the really interesting structural features within the East African margin. So we've got the Davy fracture zone and the C gap and alpha fault zones up in here, the Davy Wallu system of the Lamu basin. We have some of the interesting features of the Mozambique coastal plain, the Lobombo and Matakasabi monoclines, and you can see the large gravity low there associated with the continental fragment of the Beira High. Also, we use our magnetic data very extensively, particularly for the onshore, delineating basement fabrics, Precambrian systems, volcanics, and also, of course, for basin delineation from magnetic depth to basement estimations. Again, this is just a kind of zoom to East Africa, so you can see some of the major basement foliation in East Africa and Madagascar, and a zoom to the high-res imagery for Mozambique, Tanzania, sorry. So that data really underpins everything that we do at Getech. It's our starting point, particularly for our tectonic evolution studies. I'll just briefly run through some of the methodologies and the workflows in place, really to set the scene for showing you some of our the interesting things from these studies. So the tectonic evolution studies really it's a 4-phase workflow. So we start by compiling our data layers. So we have an extensive series of databases and data layers that principally include the structures. So the structures mapped at 1 to 1 million or finer scale, and their associated activation histories. We also have a whole range of additional tectonic data layers like digital geology, volcanics, magpics and isochrons, basins and intrabasinal features, which I'll show a few examples of those in just a sec. The second stage is to take all of those data layers and that interpretation and incorporate it into our geophysical modelling. So we run a series of 2D grav and mag profiles. Typically there are in the range of 20 to 25 per study area. So the study areas I showed before, Equatorial, South Atlantic, East Africa, particularly for this East Africa focused session today, there would be approximately 25 2D grav and mag profiles for each of those study areas. Following on from that, we feed those into our depth to basement and depth to moho grids, which are a regional grid for the whole of the study area. And then all of that is incorporated into our plate modelling, where we have now a crystal architecture database, which is, I'll show that in just a second, but that's a crystal types database based on our geophysical modelling and structural modelling. Incorporates both onshore and marginal crystal architecture. We've been doing a lot of work recently on rift mechanics and the nature of the continent-ocean transition, and obviously the implications that has for our plate model solution. And then that feeds quite nicely into our plate modelling experiments. So we would try to get the best regional dynamic fit for a study area, but that would be done consistently within our global plate model, so that there was no disruption to the global plate circuit. It's all done within our global framework. So I've just run through some illustrative images of those things I've just mentioned. So this is the current state of our structural database for Africa. It's quite a busy picture, but I hope it gives you an idea of the amount of detail that's sitting within our structural database for Africa. You can tell by looking at this image that our main focus has been the margins, but the more we've worked up the study areas, the more it's become apparent that you can't understand the way that the margin deforms and the availability of accommodation space and heat flow without understanding its links with the onshore geology and the distribution of cratons, mobile belts, pre-existing Precambrian shear zones. It's the influence of pre-existing crustal strength and rheology has become really apparent in the East African system. So you can see that we've been gradually working onshore to incorporate all of the East African rift system and the Karoo system, as well as all of the big Precambrian mobile belts and shear zones that span Africa. In terms of how we compile the structural database, it's kind of multi-phase analysis of various data sets. We start off with our Landsat imagery, doing a lineament analysis from Landsat. We then incorporate a suite of gravity and magnetic derivatives to work up a lineament analysis. Just taking you through some of the magnetics there. We then calibrate that against public domain data, so geological maps and a whole range of seismic lines, published cross-sections, P-wave velocity profiles, public gravity and magnetic profiles. And the blue squares there are just to give you an image of the footprints of all our georeferenced images, whether they be fault array maps or geological maps or other tectonic maps for this study area. So this is just a very small example. This is Tanzania, so you've got Pembrokeshire Island in there. So this is just kind of showing the amount of data we have sitting behind those interpretations. This is just an example of some of the data that sits within that lines location database, so just some published GXT lines from the Tanzania span work. And then, by doing that, and by incorporating all of those data sets, we get to a final structural interpretation with all the kinematics assigned. And because there are so many tools that we use in that interpretation phase, we try to record them all as thoroughly as possible. So all of those structures that I just showed in that previous slide have a full attribution that says where things have come from. So how the interpreter has imaged that particular feature and the confidence we have in that feature. What we've been working towards as well is giving all of those structures within the data sets activation histories. So that obviously facilitates plate modelling and geodynamic evolution. So this image here with all the blue structures highlighted is just, they are the structures in this data set from the equatorial Atlantic that have activation histories associated with them. So you can see of the overall data set for equatorial Atlantic, there were about 60% of the structures had activation histories, but that's represented by almost 90% of the onshore structures. The remainder is represented by the oceanic fracture zones. So we're working towards having all of the onshore features and marginal features having associated activation histories. Some additional tectonic data layers that we compile in that initial stage is our digital geology. So this is a compilation of various public domain geological maps plus geological interpretation from Landsat. And then particularly in the case of the older maps, we try to modify them as much as possible to our interpretation. So to our structural interpretation. We also have a in-house data set of magpics and isochrons, which are used to manually digitize our oceanic polygon data set for our plate model. We have a volcanics data set, which is primarily compiled from gravity and magnetic data. We remap or redefine all of the basins and intrabasinal features based on our gravity and magnetic interpretation. This is just an example from the Horn of Africa, which I'll show it in a bit more detail in just a sec. Which in this particular case, we've redefined a lot of the onshore basins and interpreted quite a few newly discovered basins. The geophysical modelling aspect of our workflow incorporates, as I mentioned before, it's usually in the region of 20 2D profiles which feed into these studies. So this is the coverage for Africa from our 3 most recent studies. I think they're in the region of 45 2D profiles for Africa, and this is just as I mentioned, from our 3 most recent studies, so 2013, 2014. There's a whole library of additional 2D profiles that sit within our Africa databases at Getech. The primary purpose of our 2D profiles is for defining crustal architecture. This is an example from the Namib Basin, or somewhere on the West African margin. It's as I mentioned before, we've been trying to incorporate in a bit more detail the nature of the continental ocean transition. So in this case, we've got high velocity igneous crust with a series of seaward dipping reflectors. It also allows us to map the extent of stretched or attenuated continental crust versus continental craton, and the onset of oceanic crust. We also tend to design our 2D profiles in conjugate pairs, particularly, for that example for the equatorial and South Atlantic studies where we were working at both margins. This is an example from the Santos and Namib basin, just to look at the asymmetry of the margin, the rift mechanics in the crustal architecture, the amount of accommodation space and the distribution of salt. Another application for our 2D profiles is using them as an aid to seismic depth conversion. So we had an example from the equatorial Atlantic where we had a regional seismic line that we were trying to model. It had very extensive depth to basements in the region of about 17 kilometres, and we wanted to double check that interpretation against our gravity and magnetic data. And you can see in this example that the depth to basement here, even in our deep solution, only got to about 12 kilometres to get a good fit with the gravity, but there was a massive offset between the observed and modelled magnetic data. So that was telling us that our magnetic basement was too deep in this model, and we never even got to those depths of 17 kilometres. In the absence of any major volcanics in the area, we knew that magnetic signal was telling us that actually the basement depths should be much shallower in this particular area. So this second model is honouring the observed gravity and magnetic data, where we have a much better fit between both the gravity and magnetics, and you can see that the depth to basement here is in the region of 5, I think, at its deepest point here. So it's just another application that would feed back into the velocity models for the seismic interpretation. The second phase of our geophysical modelling is to do the depth to basement and depth to moho. So it's just an example of the depth to basement grids for the South Atlantic project and the depth to moho grids. And then it's an iterative process, so they would then feed back into the 2D profiles, and we would do another round of iterations for the 2D profiles to make sure that the two are consistent across the board. All of that data then feeds into our plate modelling solutions. So this is what I mentioned previously, our crustal architecture database. I don't know if you can read this in the corner, but these were the kind of things that we're working towards incorporating into our crustal architecture database, rather than just having continental and oceanic. We wanted to make sure that we were representing the thickened cratons and cratonic blocks within the interior, which is particularly important in East Africa and the East African rift system, where predominantly Neoproterozoic mobile belts and reworking during the Pan-African orogeny what dominates the onshore. But the same in the West African margin, the difference between where the cratonic domains are very close to the margin, and the same with the equatorial, and the impact that has on the ways in which the margins can deform, the strength of the onshore regions and the way in which the margins can deform. So we are incorporating all kinds of things into our marginal database now, so serpentinized mantle, continental ocean transition, high velocity igneous crust STRs. We're trying to incorporate all of that in, so we have a more robust model for the plate model. Once we've done that, then we feed that into a series of plate modelling experiments. I mentioned before that we would run until we found the solution that satisfied the evidence, the scientific evidence, but that also satisfied our global solution rather than just it being a regional solution. So that's the methodologies, which sets us up quite nicely for some of the interesting insights or the study observations from the East African study. So I'll start with the Horn of Africa. So that first phase I mentioned, so the structural interpretation that we do has allowed us to image a newly discovered or not well documented strike slip system in coastal Somalia. Coastal Somalia and Somalia is not well explored. There are some papers from the kind of 1980s that allude to this potential strike slip motion in the Lugmandira basin, in here, the Karoo system, that there is some transpressional reactivation of the basin bounding faults in there. But that it was left at that and was never investigated further, or the extent of this strike slip system was never investigated further. On the basis of our structural interpretation, we interpret that the strike slip system is very extensive in coastal Somalia. You can see the red features highlighted here representing that strike slip motion. This hasn't showed up very well, but there are some excellent rhomboidal geometries imaged in coastal Somalia in here. I think I've got an overlay which represent that strike slip motion. Also, in our gravity data, there were some very linear features in the margin of coastal Somalia, and also, like the equatorial Atlantic example, a very steep and narrow continental margin with some transpressional anticlines in the coastal margin of Somalia. And in all models, the coastal Somalia should be an obliquely rifted, relatively wide margin associated with the southwards translation of eastern Gondwana in the Jurassic. So when did this strike slip overprint occur? We can get some clues from the onshore basins of Somaliland. So these basins in here, so Duror and Nagal, have been previously interpreted as Jurassic to Cretaceous basins. We are not too sure about the Jurassic history of these basins. We'd be more inclined to interpret them as late Cretaceous basins with some reactivation during the opening of the Gulf of Aden. This seismic example here shows that the main Synrift package in the Duror Basin, which is just up here, is Maastrichtian to Eocene, and the Jurassic to Cretaceous are relatively equal thickness. This Jurassic Adigrat and Hamelin sequences in here aren't just equal thickness in the Rift Basin, but they're very widespread in outcrop all over the Horn of Africa in relatively equal thickness. So it's telling us that they're not thickening into any Jurassic or early Cretaceous basins in here, and that predominant structuring of these basins happened in the late Cretaceous. We interpret that structuring happened as orthogonal basins that formed in conjunction with these strike slip systems in Somalia. And the causative mechanism for those is the opening of the Mascarenhas Basin in here and the northwards translation of India. You can see I've just put some big schematic arrows on here to represent that coastal strike slip system in Somalia. There has been some reactivation of that strike slip system in the Miocene, so from about 20 million years when the Aden Ridge was first in place. Ridge push forces from the Aden Ridge have reactivated this with the opposite sense of motion. So we're seeing those rhomboidal geometries at present day potentially being a result of this right lateral motion at present day. There was 1979 a very deep focal 33 kilometre focal earthquake near Mogadishu 4.9, which might tell us that this is some kind of subvertical strike slip system that's rooted somewhere near the Moho and is forming quite a major crustal boundary in this area. Staying in the same area and looking at the basins, this is our depth debasement solution from the magnetic SPI and the gravity inversion. You can see, again, same area, that there are a lot of deep solutions for the Horn of Africa compared with the rest of the East African margin, or the deep blue solutions there, and in this SPI point solution image. If I just zoom into a little bit more detail, we know about a lot of these systems in here. We know that the Anzergraben sits in here is a predominantly early to late Cretaceous system, but what we didn't know was that there is potentially an equivalent system which sits in here in Somalia and running into Ethiopia. What we didn't know was the full extent of the Karoo system. So this is the Lugmandira Basin and Mandira Basin of Kenya, which has, of course, the some big discoveries in here, the Caleb Field and the Hilala Field, which sit just within Ethiopia but are all part of the same system. That is quite extensive, coming out of the other side of the Anza Basin into the Lamu in here, and also continues up here into the Horn of Africa. So this big northeast-southwest trending Karoo system that runs all the way through here. I mean, in portions of this basin, we're getting depth to basements well over 10 kilometres. There is also a relatively newly and discovered system of basins up here that potentially might relate to this system, but of course they're showing far deeper basin geometries. So there's a series of almost east-west trending basins running up through here and maybe down through here as well. This depth to basement image also might back up what we just mentioned, that these basins in here, the Daror and Nagal, aren't showing particularly deep basement solutions. So the idea that they may have been Jurassic grabens with 10-kilometre basin fill is looking increasingly unlikely. The Gardafui system up here and the across Socotra and the Socotran platform up here, they do show deeper solutions that might be more appropriate and to associate them with similar systems to the Yemen systems in the conjugate margin. You can see just in this image here how we've delineated our basins in our and intrabasinal features in our internal databases. So that by doing those depth to basement investigations, we have 4 main phases of basin evolution in the Horn of Africa. We have the Carboniferous to Jurassic Karoo sequence, which is this huge northeast-southwest trending system that runs all the way up through here. We then have the Jurassic obliquely rifted margin of the Somali coastal basin. Then we have the Cretaceous northwest-southeast trending basins, the Anzergraben system that runs up into the Sudanese basins up here. And then we have the late Cretaceous, Maastrichtian to Eocene basins with some Oligomycene reactivation due to the opening of the Gulf of Aden. We don't only focus on the onshore basins of Somalia, so we've looked in quite a bit of detail at the margin evolution. Firstly, we were just looking at the gravity character of the East African margin, and we noticed that this section, the Majunga Basin in here, and the very northeastern tip of Somalia had very similar gravity signatures. This kind of train track system of gravity lows and highs with a large outer high before we get into what we had interpreted as oceanic crust. But of course, these two sections are not conjugate. The conjugate margin to the Majunga Basin, doesn't show any of the similarities in terms of the gravity signature. It's very different. It doesn't show that kind of parallel system of gravity lows and highs. We interpreted that was telling us something about the initial facilitation of the rift, it being very asymmetric and being facilitated by simple shear and large detachments. And that these two, the dip and polarity of the detachment in the pre-rift fit would flip along a transfer zone that lay between this section of the margin and this section of the margin, and that is likely to be a result of the onshore rheology and the distribution of Archean basement rocks in this area. To investigate that a little bit further, we designed a suite of 2D profiles, so I'm just going to highlight this profile up here, which is across that section of the margin in here. we wanted to get a handle on what the nature of this this series of marginal gravity lows and highs was. So we had two models, data-driven models. The first one is a volcanic margin model, which includes a series of SDRs in this in this area here, which were modelled to represent this bulge in here before we get into relatively planar oceanic crust on the other side. You can see that the gravity fit is very good for this example, but we also modelled it as an exhumed mantle bulge with thin COT sediments on top, which would be slightly metamorphosed at the base, and this would be serpentinized mantle in here, and you can see that we get equally as good a fit for this model. We do have some good seismic data within or relatively close to this area, particularly for the Majunga Basin. This is slightly further south than that profile, which would have been up here, would have been in the Lamu Basin. But although the imagery is excellent for the kind of continental sections, we lose the imagery slightly. It's not well defined, that continent-ocean transition area from the seismic. So we're trying to work towards a best fit solution. We'll do some more work working further south with the other 2D profiles and some in the conjugate margin before we commit to either of those models. Some other study observations from Mozambique. So we're just going to look very quickly at the Mozambique coastal plain in here, which is still quite a controversial area, particularly in terms of plate modelling. Some of the most recent work has said that rather than the Lubombo and Matakasabi monoclines, which sit just here and here, being failed volcanic margins, that they were actually successful margins, and that all of the Mozambique coastal plain is floored by oceanic or proto-oceanic crust, which would solve lots of problems in terms of plate modelling for overlaps with cratonic fragments of Dronning Maudland. But unfortunately, that was our preferred model, and in our existing Getech plate model, which I'll show in a minute, we had modelled all of the Mozambique coastal plain as oceanic crust with a series of ridge jumps which left the Beira High as a continental fragment just sitting up there. But when we did our depth to basement and depth to moho investigations, that theory wasn't backed up. The depth to moho showed, depth to moho is in the region of 30 to 35 kilometres, which isn't consistent with it being oceanic crust. Even if it was very thickened oceanic crust with a lot of volcanic addition, you can see that the depth to moho here compared to known areas of thickened oceanic crust and volcanic addition, so the Madagascar Ridge, Mozambique Ridge and the Agulhas Plateau, there's a big difference between the two. We get depth to basements of about 20 kilometres in here, but that's nowhere near what we're seeing in here. That's in good agreement with the seismic tomography results from Crust 1, which were telling us that, okay, we're going to have to do something about this. We're going to have to incorporate this being continental crust into our plate model to see what kind of implications that has for the global plate circuit. And if we were doing that, then we would have to apply that same assumption across the board and start to look at continental fragments of the Seychelles in the same way. This is what I just mentioned earlier. So this is our existing interpretation for the Mozambique coastal plain. So you can see in there we have the Mozambique coastal plain floored by oceanic crust with a series of ridge jumps, which leaves the Beira High and the Tegela microplate before we get into full spreading down here. We've also constructed a series of 2D profiles in this area to try and get a better handle on the crustal architecture of the Mozambique coastal plain and what implications that's going to have. But this is just a preliminary plate modelling experiment for that area. So we have the Mozambique coastal plain as oceanic. and all of these red fragments in here so the fragments of the Seychelles, Laxmi and Laccadive as continental fragments, and you can see that it leads to a much looser fit and quite complicated geometries for the pre-rift fit of Gondwana. It also incorporates a lot of ridge jumps, sequential ridge jumps in this area to get to our final solution, incorporating some kind of triple junctions and ridge jumps in the Seychelles and Madagascar between 80 and 70 million years. And that kind of goes against our mantra that we want to find the simplest solution that satisfies all our scientific criteria. So this is, again, as I mentioned, this is a working project at the minute, is the East African one, so it'd be great if anybody wants to talk about it or give me any insight into to what leads we should be following in terms of any ways of trying to solve these problems. It would be great to talk at the coffee break. So thanks very much.
Okay, time for a couple of questions. And if not, let me ask one. I mean, it's an interesting thing here, which I've no idea the answer to, but you kind of alluded to in some of your pictures where you show layer and layer and layer of data. But like when you look at your iPhone and you see that your history is displayed in front of you. So you can have, satellite data, airborne data, seismic data, passive seismic data, people walking over the ground collecting rocks. That's kind of one set of things. And then you've got plate tectonic models, chronostratigraphy, 2D potential field cross-sections, seismic interpretations, etc., structural grain maps. How on earth do you fit all this together? I mean, is there one model of the world, or how do you fit it all together? Because I can't figure it out myself.
With lots of arguments about who's right
so it goes
and who's
on
got
in
the
here.
best data.
I see. No, but I mean, do you hold it all in one place, in one model, or how are you doing the work, I guess, is what I'm asking.
Yeah, I mean, we're trying to incorporate it all as much as we possibly can. We try to. I mean, there is I work quite closely with a colleague of mine who is very open-minded and will say, he'll look at all of the data and then come up with his solution, whereas I tend to get an idea in my head and then look at only the data that fits my and then I get told off and go, all right, well, I'll go and have a look at all of the data.
You're probably not the first person in the world to fit things to their model of the world. Okay, no, that's good. Anybody else?